one thing that I always forget to do is start the recording. So factor that into your review. Remember to tell me to start the recording. Okay. So I want to send the recording back to you. So I just missed that whole first problem that we worked. Darn it. What I'll do is I'll flip the board over and then we'll recover it real quickly. Okay. But as I was saying, did anybody get any particular good deals on the book, like renting or anything like that other people might want to know about? Oh, my other thing is put up the chat. So don't forget to sign in the chat. Looks like a whole bunch of people have signed in already. Excellent. Thank you very much. Okay, good. Darn it. You know, before we started, I was looking at that record button and saying, oh, you got to remember to hit the record button. And of course, I forgot about it. Yes, go ahead.
I got a free PDF file of the whole textbook for the elementary and the which one was it? Let me see.
You got a free PDF download of the text?
Yep.
Okay. And where'd you get that? Through what site?
I don't remember. My girl helped me get it. She just sent it to me. I was like, oh, okay, I guess that's the one.
Okay, good. Well, if you can get back with her and figure out where she went to get the PDF download. I think somebody else did that also.
For sure. No, well, if I get the link, then I'll send it to the chat.
Yeah, that's a good idea. Do that. Yeah. Send the link to the text. Or if you don't get it until after the class starts, then just email it to me and I'll put it in the homework assignment.
Yeah, for sure. Yeah.
Okay, so let me drop back and just do a quick review of the previous problem. Luckily, we didn't erase it, but I did erase the review. Phooey. Okay, anyway. Bonehead I am. I got to try a string around my neck, I think, to remember to start the darn recording. Okay, anyway, so this was the first problem that we worked in tonight's lesson was 8.3, example 3, which is a value mixture problem. So that's where we're mixing tea and almonds to get this blend. And so I set up my table right here, and it's based upon the relationship, the cost relationship. So this is called the value mixture problem. And we use the cost relationship in it. Let me go over here. I believe I forgot to do that. Okay, hang on. Let me get out of the way. Okay, so our table is based upon that relationship. So the amount times the price is equal to the cost. Down this side right here are the two things that we're looking for, tea and almonds, and we're going to make a mixture of those two. Okay, so I fill in everything that I know. So they gave me the unit prices of all of the items. So the tea was $4.30, the almonds was $1.30, and the mixture was $3.50. And so I write all that in. And then I write my variables because they gave me a total amount that I'm going to make. They said I'm going to make 300 ounces. So I put that over here, 300 ounces. And the tea, I used T as the variable. The almonds, I used A as the variable. So I got the T and the A, and that adds up to 300 ounces. And then the only thing I don't have is the cost column over here. So I just follow my relationship across. So this times this is equal to that, 4.3 T. A times 1.1 is equal to 1.1A, and then 300 times 3.50 is equal to 1,050. And then I got my two equations. They fall right out. So here's equation 1, here's equation 2, and that gives me a system. And then I elected to solve this system using the elimination method. So I wrote down the system, put a line under my original system, numbered my equations, and then to our elimination, we decided to eliminate the variable A of the A variable for almonds. And so then I just needed to multiply equation 1 then by negative 1.1. So I went through and did that, multiplying every term by negative 1.1. And then I added the two equations together. So I got 3.2 T is equal to 720. The A's dropped out, and I got T is equal to 225 ounces. Okay, and then I just went back to equation 1 up in the upper right-hand corner there to solve for variable A. Okay, and that was a quick review. Good. All right. Okay. Now, next time, someone remind me to start the recording. Don't just write it down in the chat because I might not read that, but say it out loud. Hey,
All right, I got you.
start the recording, please. Okay. Thank you. I will. All right. All right. So now we're going to work another word problem. This is example 4 in section 8.3, and this is an interest mixture problem. Okay, great. All right. So we're up to speed. The only thing I missed out on was the review. Okay, wait a minute. Where's my book? Oh, book is over here. Okay, so here's the book. So example 4. So now we're at the very bottom of page 521. So it says, Ronnie's student loans totaled $9,600. Part was a plus loan made at 3.28% interest, and the rest was a Perkins loan made at 5% interest. After 1 year, Ronnie's loans accumulated $402.60 in interest. What was the original amount of each loan? Okay, so what we want to know is how much did she originally get of this $9,600? How much was in each of the different loans? That's what we want to find out. Okay, so basically I sort of set it back to myself, so I think I understand it. And this is a perfect one for a table. So this table uses the IPERT. Interest is equal to a percent a principal times the rate times the time. Again, we'll put that in up here so you get a chance to see it. So once again, I got my items. These are my 2 loans over on this end right here. And then coming down this way. Okay, I got the plus PLUS and the Perkins. I'll call it the perk. And then you always have a total or a mixture. I could put mixture in there too, but I'll use total this time. So our relationship is this. I is equal to P R T. Interest is equal to the principal times the rate times the time. Okay. So I'll just use the letters to abbreviate what we're looking for. So we got the P times R times T is equal to I, the interest right here. Now the T that we're looking at is just 1 year. So I just got a very small column for that. And that's just 1, 1, 1, okay? But now I can fill in the rest of it. So the rate, so I do have the interest rates. So it said the plus rate was 3.28%. So I write in 3.28, okay? And then the, what was the other one? Oh, 5%. Now, the problem with this is I'm going to make this box a little bit larger right here, and I'll show you why. There we go. There. Then I'm going to make this over like this. Okay. Now I made that larger because the interest 3.28%. That percent means divided by 100. So I have to put this in as a decimal or a fraction. So this is 0.0328. Okay, so that's what I have to put in right here. Because I can't just put the percent number in there, I have to change it to a decimal or a fraction. And that's one of the rules of working with percents. So this is 0.0328. And the other one was 5%. Well, at least that's a little bit easier. This is 0.05. Okay. And then down here, for I don't need anything there. Okay. And then I know my total amount of loan was 9,600. I think that was right, wasn't it? Yeah, 9,600. 9,600. So that's the plus. We'll say L for plus, and the perk, we'll say K for perk. Okay, because they both begin with P. I could use X and Y also, but I'll use those two right there. And then I got to go straight across right here. Now, they did tell me the total amount of interest at the end of the year. So that was $402.60. So 402.60. That goes right there. And then I'm going to follow everything across that way to fill out the end right there. This one, I don't have to do that because I don't know that there's no like mixture percent rate or anything like that. Like there was a mixture cost for the cost mixture problem. But now going across here, so I get 0.0328 L and then 0.05 K for the perk. And now everything's filled out. So my two equations come out the same way. So here's one right here. Here's equation one. And then equation two is over here. There's equation two. Okay, now the equations are made from that third thing that I said. All of them use the whole is equal to the sum of the parts. So here the whole amount that I took out in a loan is equal to the sum of the two different loan parts in there. The whole interest is equal to the sum of the interest from the first loan plus the interest from the second loan. So that's the whole is equal to the sum of the parts when I go down like that. All right, now I'll write my system. So here's equation one. So equation one, I got L plus K is equal to 9,600. And then equation two, I have 0.0328 L plus 0.05 K is equal to 402.60. Okay. And there's my original system right there. Okay. Let me go erase this stuff over here. Now, this one has some weird decimals in it. So that one 0.0328 is not a friendly decimal. So I have some options here. One, I can keep it in decimal form, or two, I can remove the decimals.
Remove the decimals.
Remove the decimals. Okay, that's the easiest thing. Now, to remove the decimals, when I do this, unfortunately, I'm going to end up with some rather large numbers, but that's okay. I can deal with it. I can deal with there's no decimals in it. If they're bigger numbers, that's fine. I can deal with that. So what I need to do is multiply equation two by a power of 10. And you multiply it by the power of 10 with zeros equal to the most number of decimal places. So notice the most number of decimal places is 1, 2, 3, 4 right here. Notice there's 4, here's 2 here and 2 here. So I have to multiply it by a 1 with 4 zeros. Okay, so I'll show you what we're going to do here. So I'm going to go 1 with 1, 2, 3, 4 zeros times equation 2. And what that's going to do is move my decimal places 4 places, 1, 2, 3, 4 over there. So I'll have 328 L plus 50 plus 50 K is equal to 402.600. Okay, so that's 4,026,000. So larger numbers, but now the decimals are gone. Okay, So now I want to think, how am I going to solve this? So before we used the elimination method. So you want to use the substitution method on this one?
Yep.
Okay, so let's see. What variable should we substitute? It looks like
Or K, I mean K.
the K might be the easiest one to substitute for.
Yeah.
Okay, so I can do that. So what I'm going to do is get equation 1 right here. And I'm going to solve it for K. So then I get K is equal to 9600 minus L. Okay, there we go. Put a line under that. So now I've rewritten my system. So now it's set up for substitution. So what I'm going to do is substitute into that first equation right there. Now I got to be careful when I write down the numbers in that, because the numbers are going to be rather large, but I think we can deal with it. All right, so let's go up and take equation 2 up here. And we'll do the substitution. So I'll have 328L plus 50 times 9600 minus L equals, and then it equals what? So it equals this great big number right here, 402,60000. So equals 402, 6, and 4 zeros. I think that's right. Boom, boom. Is that right? No, 6 and 3 zeros. 3 zeros. There we go. 6 and 3 zeros. Okay. So 402, 6, 1, 2, 3 zeros. 402, 6, 1, 2, 3 zeros. All right. So now I'll eliminate the parentheses and put my like terms together. So I'll have 328L minus 50L plus 50 times that, whatever that happens to be. So let's see what that happens to be. So clear. So I got 50 times 9600 equals, and that's 480,000. And that's equal to this right here, 402,600. So now I'll combine like terms. So 328 minus 50, just taking it one step at a time. So I got 328 minus 50 equals, and I get 278L. 278L is equal to. So what I'm going to do is take this number here and subtract 480,000 from it. Okay. Don't let the big numbers worry you. So I have 402, 6,000, good, minus 480,000, 480,000, right, equals what? Equals 3546 and 000. So equals 3546,000. Boom, boom. Okay, that sounds right. So then L is equal to 3546,000 divided by 278. So I'm hoping that's a whole number, but let's go ahead and see what that gets. So I get division by 278. 278 equals, and I got, no, that doesn't sound right. I got 12,755. So that doesn't sound right. Nope, So I made it, so somewhere along the line, I probably made a math error. So now though, I have everything really well organized. So let's go ahead and review everything. Make sure I did everything right. So I got my two variables right there, L and K, and that's equal to 9,600. Okay. Let me verify that. Yep, 9,600. And then I got my interest rate. So 3.28%. Oh man, that was the nasty one, 3.28% and 5%. Okay. So 3.28% is 0.0328. 5% is 0.05. And then we got 0.0328L plus 0.05K is equal to 402.60. Okay.
You added
so
an
I got my
extra
two
zero
systems.
on 4026000. Should just be 4026000.
Which one?
In
Oh, right
equation
here?
2, yeah.
4026. I put in too many zeros. Okay, that makes sense. So there should be just that many zeros in there, right? 402600.
Yeah.
Okay, good. Okay, that should do the trick there. 402600. So we'll check that right there and right here. Good. Okay. And then we'll come back here and check this. So then I will have, well, I'm not exactly liking that because that's going to give me a negative result. So my substitution here, K is equal to 9,600 minus L. So then I'll have, I multiplied this by,
It should be 32.8.
well, it's 32.8 if I multiply it by 1,000. So let me go back. So hang on. Let's go back here. So somewhere in here, I made a basic math here. So what we're going to do is go back. I'm pretty sure I'm okay up to this point right here. Okay. Now, if I want to get rid of the zeros, now, okay. So if I multiply by 1,000, that will give me 32.8 here.
So sorry,
And,
I was wrong on that. You had the
there.
the zero after 402,600 should be an extra zeros there, but it should be
This should be
500.
500K. This should be 500K right here because I move it 4 decimal places. So there's 1, 2, 3, 4. So there's my mistake right there. So I back up here, go over here. So this should be 500K because I moved the decimal point 4 places. Then that's equal to, so over here I got 4026123. 1, 2, 3, 4. Yeah. Okay, so there's still 4 zeros right there. Okay, now I think it'll come out okay. So let's see what we get now. Yeah, because I made that mistake in here. Okay, good. So then I'll get coming up here. Bring it up here. So I get 328L plus 500 times 9,600 minus L equals, and it equals this. So I'm still multiplying by a 1 with 4 zeros. That means this decimal point moves 4 places. So 1, 2, 3, 4. So that's correct. 4026000. 4026000. Okay, good. Excellent. Now I'll remove the parentheses. Oh, this should be an L. This should be 328L. Okay, good. So now let's remove the parentheses. So I'll have 500 times 9,600. So 500 times 9,600 is equal to, oh, good, that's better. So now I got 4,800,000. So that makes it match up with the other number better. So I'll have here 328L minus 500L plus 4,800,000 is equal to 402,600. Good. Now everything's going to work out. So I got to be careful. I made that one error right here because I didn't shift my decimal point enough. So let's see what we got. So now I get 328 minus 500 equals, and that's a negative 172. So I got negative 172L is equal to, so on the other side, I'm going to have a negative number also. So I got 402,623. Is that correct? 402,6123, 402,6123. Yep. Minus 4, 8, and 5 zeros. 1, 2, 3, 4, 5 equals, and I get negative 77, 4,000. So minus 774000. So L then is going to be a positive number because I got a negative divided by a negative. That's good. So I got this number here divided by 172. 172 equals, all right, and I get 4,500. So that's the amount of my plus loan right there. Okay. So you see, sometimes, especially if I got decimals, like really weird decimals, like on a test, I would never give you a weird decimal like that. I might give you 3% and 5%. So keeping it simple, because I just want to make sure that you know how to do the basic technique. Okay. Then to find K, I just go back here to equation 1. So equation 1, K is equal to 9,600 minus 4,500. So K is equal to, what does that come out to be? It looks like I need a 1 there and a 5 there. So 5,100. So that's the amount of my 2 loans. Okay, but again, we use the table method to set this one up. Okay. Unfortunately, when I eliminated the decimals, because of this one really weirdo decimal like here, 3.28%, that made the problem come out with really large numbers. If I would have had like 3%, 4%, some nice, easy round percentage, then the numbers would have been a lot more reasonable. But you see how easy it is to make a mistake. Okay, and here supposedly I know what I'm doing, and it's easy to make a mistake. Like forgetting to turn the record button on. What a bonehead I am. Okay, so what we're going to do now is take 10-minute break. So I need 10 minutes to go into the other room and beat myself up for not turning the record button on. And then we'll come back and we'll pick it up right there. And we're going to look at the next one is a percent mixture problem in example 5. Mixing of all nice things, fertilizers. Yay. Okay. So let's take 10. Okay. So what I'm going to do is put us on pause here for our 10-minute break. Okay, that sounds good. All right. So we're going to start back in 8.3 again with another word problem. Again, word problems are sort of the bane of most algebra students. So this is a good section where we're actually working these individual word problems. So you can look at different techniques and especially how to use this table method to set them up. So let me flip over to the other side here. All right. Okay. All right, so this is 8.3, example 5, which is going to be a percent mixture problem. Okay, good. So it says, let me read it. Oh, let me get back over here again. Okay. So it says mixing fertilizers. Yay. Nature's Green Gardening Incorporated carries 2 brands of fertilizer containing nitrogen and water. Gentle Grow is 3% nitrogen and Sun Saver is 8% nitrogen. Good. So some nice easy percentages. That's good. Nature's Green needs to combine the 2 types of solution to make a 90-liter mixture that is 6% nitrogen. How much of each brand should she use? So you can see this is very similar to the T mixture problem, only instead of mixing values, we're mixing percentages. Okay, so once again, this lends itself to the table method. Okay, so in this particular one, let's see, there's our interest. Okay, so the relationship is the part is equal to a percent times the whole. Okay, hang on, let me get through here. There we go. All right. So my item so here across the top is my relationship. And what that is the whole times the percent equals the part. Okay. And so what do I got? So I have the 2 types, which are what again? Let me see here. So I have Gentle Grow, which we'll call G, and Sun Saver, which we'll call S. Okay. So I got this Gentle Grow and Sun Saver. Okay, good. And now I'm going to fill in. And down here I have, once again, I'm mixing the 2 together. So I'll just put mixture, just like I did for the cost mixture problem right before. Okay. So the percentage, they gave me the percentage. Once again, I got to enter them as a decimal or percent. So the gentle grow was 3% and the other one was 8% nitrogen. So here we have 0.03 and 0.08. And then we're mixing the two together to make a mixture that is 6%, 0.06. Okay, so here I got G, S, and down here, how much of the stuff am I going to make? Oh, 90 liters. So 90 liters right there. Okay, good. And then I just have to follow out my last column. So you can see it's very similar to the T mixture problem. So this times this is equal to this. So I got 0.03 G, 0.08 S is, whoops, let's see, times there is equal to, so I got 90 times 0.06, 90 times 0.06 equals, equals what? Equals 5.4. That was what I thought equal. Okay, 5.4. Okay, good. So at least my numbers will be a lot more reasonable on this problem. My equations come out the same way. So here's an equation right here. And then right down here, here's another equation over here. So then I'll write down my system. So we got number one, G plus S is equal to 90. And number two, I got, 0.03 G plus 0.08 S is equal to 5.4. And I'll put a number under it, a line under it. That's my original system. So I think on this one here, I will get rid of the decimals. So to get rid of the decimals, what do I need to multiply equation 2 by? Anybody?
100.
100. That's right. A 1 with 2 zeros. So I have 2 decimal places. So a 1 with 2 zeros. So I'm going to go, let's see, 100 times equation 2. So that'll give me 3G plus 8S is equal to 540. Okay, good. I think I did all the decimal moving correctly that time. So now I want to sign, now I'm going to look and see, how do I want to solve this one? Again, this one might be an easy one to solve by elimination. Okay, I could do it by substitution also, but let's try elimination. So I'll try and eliminate the S variable right there. Or no, let's do it even easier. Let's eliminate the G variable. It doesn't matter.
Does it matter which way we pick ever?
No, not unless I tell you specifically which way to solve it. Like on a test, for example, I might tell you to solve this one by elimination or this, but typically on the word problems, I'll just let you choose your method.
Okay, thanks.
Okay, so let's multiply equation 1 by -8. So if I do that, that gives me -8 G minus 8S is equal to negative 720. Okay, then I'll add the two together right here, 1 plus 2. And here I'll get negative 5G. The S's cancel out, is equal to negative 180, I do believe. Let's see, there's a 0, there's 12, 6 and 1 is 7. Okay, so that turns. So G then is equal to a positive 180 divided by 5, which is equal to what? 36, huh? Is that right? So 3 goes in there, 15, 30, 36, I think. I think that's right. So 36 liters. Okay, so that's my one variable. That was nice. So that's more like the one that I might give you, say, on a test that'll have nice, easy round numbers right that'll work out very easily. And then for S, I just go back to equation 1 right here. So going back to equation 1, I got S is equal to 90 minus 36. So S is equal to what? To 54 meters. Okay. And then down here, I got my G right here at 36 liters. Okay. Let's see, did we get that one correct? I don't know. Let's see. Okay, and the author goes through the exploring the concept on there is more confusing than it is anything else. Just go by the pure mixture thing. We're mixing two things together to make a third thing. Just like the cost mixture problem, only instead of cost values, this is percent. That's it. Okay. Let's see. All right. Did we get it right? I do believe we did, and we did. We got it right. Okay. Now, the last one we're going to look at, we're going to look at two motion problems. So motion is another one that throws people usually. So we'll look at a couple of motion problems. And what's our motion relationship? It's the dirt equation. Distance equals rate times time. Okay. Let's go back over to this one, and we'll clean this board up here. Okay, good. And we are going to look at what? At example 6, which is a motion problem. This is train travel, but it doesn't make any difference. This could be bicycles, it could be cars and trucks, it could be airplanes, it could be people walking or running, canoeing, boats, anything. Anything that involves motion will involve this same relationship and basic idea that we're going to do right now. So this is called example 6, a motion problem. So 8.3, example 6. A motion problem. Okay, good. And let me go ahead and read it here. All right. And this involves trains. Okay, but that's okay. Trains, planes, and automobiles, as the movie said. So here we got a Vermont Railways freight train leaves Boston heading to Washington, D.C. at a speed of 60 kilometers per hour. Kilometers per hour, kph. Okay. 2 hours later, an Amtrak Metroliner leaves Boston bound for Washington, D.C. On a parallel track at a speed of 90 kilometers per hour, 90 kph. At what point will the Metroliner catch up to the freight train? Okay, so can I say it in my own words? Okay, so we have these two trains on parallel tracks. They both leave from the same place, going to the same destination, but at different speeds. One's at 60, one's at 90. And the faster train leaves 2 hours later because it's faster. And so at some point, it's going to catch up to the slower train. And we want to know what that is. What's the time? What's the distance that it will catch up to them? Okay, so I said it in my own words. All right. But once again, we can use the table method to help us put this together. Okay. Hang on just a minute. Let me straighten out my notes right here. Okay, good. All right. So here my item. Oops, hang on. Yep, there we go. Okay. Okay, so what do I got? I got the Vermont train, I think. Yeah, Vermont and then the Metro. Vermont Metro. And once again, as always, I'll have a total down here at the bottom. That comes into play somewhere along the line. So now my relationship is the motion relationship. Distance equals rate times time. D equals RT. Two adjuncts of that, the rate is equal to the distance divided by the time, and the time is equal to the distance divided by the rate. But this is our primary one right here. That's the one that I'm going to put in my table right here. Okay. So again, I'm going to have the rate times the time is equal to the distance over here. Okay. So I don't know the distance, right? But if you visualize it, it's going to be the same for both of them. So here's their start in Boston. And then they're going this way to end in DC. Okay. But there's two trains. So here's the Vermont, the slower train, and then the Metro, the faster train. And they're both going on parallel tracks. But at some point right here, at some point, D for distance, they're going to miss up. They're going to mix, they're going to meet up. So it's going to be the same distance when they meet up. Okay. So over here, this is the same for both of them. We don't know what it is, but it's the same. Okay. Now I do know their rates. So let's put in the information that we know right here. So the Vermont, I think, was the slower one. Let's see. Vermont was 60. And the Metro was 90. And I don't need anything down here for the total. Now, the time is the big factor. We don't know the time it's going to take. Okay, but think about this. Who's on the track the longest? Who has the longest time on the track? Is it the faster train or the slower train? What do you think?
Vermont.
The slower train is going to spend the longest time on the track, right? And their time difference is 2 hours. So that means if the, and you can do this both ways, but here, if the Metro is on for time T, then the Vermont is going to be on for time T plus 2 hours more because it's 2 hours longer on the track. Does that make sense? And then I don't need anything down here for the total. Okay. Some people will put T minus 2 on this one here and T up for the Vermont one, but I sort of like to work in plus signs if I can. So now I just follow this across like this, and both of these are equal to the distance right here. Okay, and I don't know what that distance is, but it's the same for both of them. So this times this equals that. This times this equals that. Now, in this one, where do your equations come out? So the equations, instead of coming out this way vertically, they come out horizontally. We're going to do them both inside here. So here's equation 1 right here. There's one equation. And then here's my second equation down here. There's my second equation right there. Let me write them down. So here's equation 1. Equation 1 says that 60 times T plus 2. Now remember, that's a binomial, so I have to put it in parentheses right there, is equal to the distance that they meet. And equation 2 says that 90t is equal to the distance that they meet. There's my system. 2 equations and 2 unknowns, d and t. And those are the 2 things that I want to know. How far out from Boston did they meet, and how long did it take them to get there? Okay, so the question is, what method are we going to use to solve this?
Substitution.
Substitution, right. What are you going to substitute?
The first equation, right?
Notice, what are they both equal? They're both equal to the same thing, d, right? So I can just say this one is equal to this one. 1 equals 2.
Yeah.
Can I say that? They're
Yeah.
both equal to d. D equals d. Notice distance, distance. So d is equal to d. So I can say 90t is equal to 60 times t plus 2. And now I got 1 equation and 1 unknown, because the distance is the same. Does that make sense? Okay, I'm not using any magic tricks. All I'm using is some common sense. But drawing this sort of picture up here helped me put it together. So I could see the 2 trains, and sure enough, the distance, they both go the same distance, even though they're not on the track the same amount, but they both go the same distance. So now I can eliminate the parentheses right there. So I got 90t is equal to 60t plus 120. So 90t minus 60t is equal to 120, subtracting 60 from both sides. Combining like terms, I get 30t is equal to 120. So t is equal to 120 divided by 30. T is equal to 4 hours. Now keep in mind this kph, kilometers per hour. So the time is measured in hours, not minutes. Okay, so it's going to be 4 hours on the track. But how far is it? We'll just take the easiest one, number 2 right here. So taking number 2, I get 90t is equal to d. So d then is equal to 90 times 4. D is equal to 360 kilometers. Okay, because they're both going kph or kilometers per hour. And that makes sense. Okay. So did our thought process for setting this one up. Most people get confused by the time factor. So the easiest way on that one is think about who's on the tracks the longest, who's moving the longest amount of time. And here is the slower train is on the tracks the longest. Okay. So if the faster train is on for time t, then the slower train is on for time plus 2 hours more. Okay, so they're on the track for 2 hours more. Okay, does that make sense?
Yep.
Okay, good. And you can see that worked itself out pretty easily. Nothing difficult about that one. Now, the next one that we're going to work out, the next motion problem, is a little bit more confusing because it has another factor in it. Yeah, go ahead. What's your question?
Let's say like you get another different equation, right? With the equation going to the right instead of going downwards. Would it be theoretically like the same, like the distance or like the ending part would be the same? So you'd have to do the exact same equations kind of towards the end? Or
No, I don't quite understand what your question is again, Antonio. What is it?
so you're like the equation right from Vermont and then the metro right to the right. The equation is going from left to right instead of from top to bottom. Like the
Yes.
equal, so it'll
this
equal the
time in the
deep, right?
motion, the motion problems, typically they go in this direction here.
Okay, yeah, that's what I was
From
just
left to
trying
right.
Yeah.
Whereas in the value and percent mixture problems, they go from top to bottom.
Okay, yeah.
But you sort of got to play it by ear and just sort of think about which way the equation might go.
For sure.
And that's the organizational factor of the table. So if I fill it all out and I use the relationship to fill out the missing boxes, then typically you can see where the equation is, the final equations.
Yep.
Okay, let's work another one here.
Thank you.
Okay, let me clean up this board. All right. Okay, good. We're doing good. I think we're going to even get into 8.4, which is really good. So I'm sort of shooting for that. All right. So this is 8.3, example 7. Again, a motion problem. Okay. But this one involves two things that are affecting the speed. Okay, so there's another factor in here, and it's the wind factor. So let me read this one. So this says a Boeing 747 jet flies 4 hours west with a 60 mile per hour tailwind. Okay. Returning against the wind, it takes 5 hours to come back flying against the wind. Find the speed of the jet with no wind. Okay, so here, this one might help if you sort of sketch out a little picture of this one. Again, it doesn't have to be very well drawn out, just a little stick figure. But here it's going through 2 points. So the distance is the same. So once again, the distance is the same. So we got a place here and a place here. And it goes between the 2 places. Okay, so on one distance, if going this way here, here's my jet. Here's my jet. Going real fast. Okay, and it's going at some speed, which I'll just call R, for distance equals rate times time, right? But in this distance here, it has a tailwind. So the wind is going this way at 60 mph. And the time for this leg is equal to 4 hours. Okay. But down here, it's coming back. Okay, so there's my jet coming back right there. Again, it's going at the same rate. So there's its rate right there. So it's going at the same rate, but now it's going against the wind. So the wind is going like this way at 60. And it takes T is equal to 5 hours. Okay, so that sort of helps me visualize the problem. But again, I'm going to use the same thing, the dirt relationship, distance equals rate times time. Okay, so my 2 items, and I have 2 items. I got with the wind and against the wind. So here's with, and here is against. And then as always, Even if you don't use it, always put the total down at the bottom right here. Even though you can see in the last problem, we didn't use it at all, but that's okay. But get in the habit of putting it down there, then that makes a complete table. And if you don't use it, you just scratch it out. So my relationship goes across the top. So here's the dirt relationship. So the rate times the time is equal to the distance. And once again, the distance is the same. So this distance, D, is the same for both trips. And that's nice. That's a nice factor. So here the rate. So with the wind, it's going to be R plus 60. Does that make sense? So I got a 60-mile-per-hour tailwind. And it took, okay, use my blue one for these, for filling in the different items right here. Okay. So this one here is R plus 60, and it took me 4 hours. Okay, and then I went distance D. Okay. So this times this is equal to that. Then down here, it's against the wind. So it's R minus 60, and it took me 5 hours. But once again, I went D. You notice down here, I didn't use any of those. So I'll just put I'll just cross those out. Okay. But once again, my two equations are right here. So here's one equation right here. And then my other equation is down here. Okay. So now I can write down my system. So now don't forget, you got to use parentheses because this represents one item. So I have to enclose it in parentheses. So equation 1. So I got the rate times the time. So I got 60. Ah, dang it. Hang on just a minute. We got R plus 60 times 4 is equal to D. And 2 down here, I got R minus 60 times 5 is equal to D. So once again, you can see this lends itself to solving by substitution. D equals D because the distance is the same. So I just set these parts equal to one another. So I have 4 times R plus 60 is equal to 5 times R minus 60. Okay. Everybody up with me up to this point, how I set it all up? And this is the same. You'll see this with boats, for example, boats and water current, canoes and water current, for example. They'll all use this same sort of thing because they know the wind factor or the current factor messes people up. Okay. So now I just eliminate the parentheses down here. So 4R plus 240 is equal to 5R minus 300. Good. So I think that I will, I'm going to subtract 4 and add 300 to both sides. So what I'll get then over here, I'll get 240 plus 300 is equal to 5R minus 4R. All right, it can't come out any easier than that. So then finally down in this last equation, I get, what is that? 540 mph is equal to R. Okay. So does it make any difference which side of the equation that your variable is on?
Nope.
No, it doesn't make any difference because it's an equation. So it's the same left to right as it is right to left. Okay. But there it is. So that's the airplane speed with no wind, 540 miles per hour. All right. Does that make sense on that one? Good. Excellent. Now we're doing excellent. Very good. So any questions up to this point on our word problems? I know word problems usually mess people up. They don't know how to approach word problems. But if you approach it with one of the techniques that we covered, either using keywords or using a table to help you set up the problem, you'll be okay every time. All right. Instead of just slinging numbers around and trying to come up with equations. Okay, good. So let's do this. And we're going to go over now to 8.4, where we're going to talk about systems of equations in 3 variables. So far, our system of equation only had 2 variables. So now we're going to add an extra variable. All right. Makes it a little bit more challenging, but not too much. Okay. Let me turn over to my notes there. So this is 8.4, solve a 3 variable system. That's what we're looking at here. Okay, put that right there. This over here. Okay, good. Okay. Right. Okay, good. So 8.4, solve a 3 variable system. So let me flip the board over here and we'll clean it up. So now we're on 8.4 over on page 832, systems of equations in 3 variables, or solve a 3 variable system. That's what we're looking at. Okay. So in a 3 variable system, we're going to need 3 equations in 3 variables. Okay. All right. So our system then is going to be comprised of 3 equations in 3 variables. Okay, so typically it might look like something like this. So our equations are going to be in what we call standard form. So AX plus BY plus, let me go to the next line down. I'm running out of room right here. Hang on. AX plus BY plus CZ is equal to D. Okay, where X, Y, Z are our variables. And A, B, C, D are our constants. Okay. So the first thing we want to look at is checking a solution. And that's actually objective A right here. It says identify solution over on page 532. So objective A is to check a solution. Okay, hang on. I'm out of ink right here. Wait a minute. Okay, good. Okay, got a fresh pen right here. So to check a solution, just like we did in a 2x2 system, okay, in two equations and two unknowns, what do? So one, we substitute. And to substitute, we use parentheses, and then two, we do the math. And there's our method. And if the left side equals the right side, then voila, we have a solution. Okay. Now, this system, okay, is three equations and three unknowns. So the system is called a 3 by 3 system, which we write as 3 big X 3. So it's called a 3 by 3 system. So two variables is called a 2 by 2 system. Okay. And that'll come into play later on, especially when we solve these things with matrices, which we're going to do in the not too distant future. But first, we need to check a solution. So let's look at an example right here. In example 1. Make sure I got the right one here. I do. Okay, good. So let's do an example of that. This is example 1. So it says we want to check this. Hang on, check these values. Wait a minute, I got to get this over here. So we have, what do we have? We have 3 halves, -4 and 3. 3 halves, -4 and 3. Okay, now, let me give you another name here. So this is called an ordered triple. So in a 2 by 2 system, it's called an ordered pair, right? So in a 3 by 3 system, it's called an ordered triple. I'll write that right here. O-R-D-E-R-E-D. Now that's not very good at all. Hang on. O-R-D-E-R-E-D-T-R-I-P-L-E, an ordered triple. So an ordered triple is now this is a 3-dimensional coordinate system that we would graph this in, but we're not going to do that. Okay, we're just going to solve these by a combination of substitution and elimination. Okay, so let me write down the system. Once again, we number the equations. So here's our system. So we have 4x minus 2y minus 3z. 4x minus what? 2y. 2y minus 3z is equal to 5. 5 and 2 is -8x minus y plus z is equal to -5, -5. And finally, equation 3 is 2x plus y plus 2z is equal to 5. And then I put a line under it just like I did before. So that's how I write my system. So the author is really bad on this in the book and doesn't write it like this. So the author doesn't number his equations and doesn't put a line under the original system. But that's the original system. So I have to check each of those variables in each of the equations. But these are pretty straightforward, so it should come out very easily. So let's see. So now we're going to do the check. Okay, so I'm going to check equation 1. So I'm going to go 4 times 3 halves minus 2 times y, which is -4, minus 3 times z, which is 3, and that should be equal to 5. Okay, so you can see it's just arithmetic. But one of the things you want to get in the habit of doing is using parentheses to substitute. Okay, so I always want you to use parentheses to substitute. So here, that's going to be 2. So I get 6 plus 8 minus 9. Is that equal to 5? So that's 14 minus 9 is 5 is equal to 5. So that checks out right there. Okay, so it checks. Okay. All right, so let's do equation 2. So equation 2, I got -8 times 3 halves minus y, which is a -4. Notice I got a minus there. So you can see where it's important to use parentheses because it's going to keep your negative signs straight. Okay. And then I got minus y, plus z, which is 3, plus 3. And is that equal to -5? Okay. So here that 2 will go into there 4 times. So I'll have -12 plus 4 plus 3. Is that equal to -5? And it checks. So here I got -5 equals -5. Okay, so that checks. And then finally, we check the last one, 3 right here. So I'll have 2 times 3 halves plus -4 plus 2 times 3. Is that equal to +5 once again? Okay. So here the 2's cancel out and I get 3 minus 4 plus 6. Is that equal to 5? 5 equals 5. Checks out. So there I ran a check and I substituted in each of the 3 equations to make sure that they all checked out. So remember, if I tell you to, like that, just like in the 2x2 system, if I tell you to check a potential solution, it doesn't mean to solve the system. It means to do this: substitute, use parentheses to substitute, do the arithmetic. If the left side equals the right side, then it's a solution. Okay, so now we're going to cover a basic methodology that we can use to solve a 3x3 system. So it's not as straightforward as a 2x2 system. All right. So now we're over at objective B, solve the system. Okay. So I'm going to give you a methodology to follow in order to do this. But if you follow this method, it'll work every time. Okay, so let me clean up the board here. Okay, there we go. So now we're at objective B right here. So we're going to solve a 3x3 system method. Okay, so let me give you a little method to follow here. So the first thing what we're going to do is to write all of the equations in standard form. So that means that ax plus by equals c. And you want to make sure, just like I did before, you line up all the x's, you line up all the y's, you line up all the z's, you line up all the equal signs, and you line up all the d's on the other side. So everything is lined up and you put a line under the system. So we're going to write this system in standard form. So that's the first step right here. One, write in standard form. I'll have to abbreviate to fit everything in right there. And then two, the second one here is we want to clear any fractions or decimals. So two, clear fractions and decimals. Okay, so we want to eliminate the fractions and decimals. That's just going to make the system easier to work with. And then three, we're going to eliminate one variable from two equations. Three, eliminate one variable from two equations. Four. Okay. Then I need to eliminate the same variable from two other equations. Yeah, let me move around here a little bit. Come over this side here. Eliminate same variable from two other equations. Okay, and it just has to be a different combination of two equations. One of the equations could be the same in both of them, but the other equation needs to be different. So I got two separate sets of equations. It's two 2x2 systems. That's what I'm trying to do, to eliminate one of the variables. Okay, and what that will give me is a 2x2 system. So I'm going to solve the 2x2 system that I get. 5, solve 2x2 system. Okay, so we know how to do that. We can use elimination or we can use substitution, but we're going to solve the resulting 2x2 system. Okay, so once I do that, I can solve then for it. So that'll give me two of the variables. So I go back, use any equation, and I solve for the third variable. And then finally, the last thing, as with any of my systems, once I get the solution, I check it in the original system. Okay, so that's a methodology to follow to solve a 3x3 system. Okay, good. And as always, I want to number my equations, and I want to say what I'm doing each of the time, anytime I work on one of the equations. Let's see. Okay, let's look at an example. So this is example 2. Okay, pretty straightforward example. Make sure I got the same one as in the book right here. We're looking good. Okay. Example 2. Yep. Yep. And yep, looking good. Okay. So I'm going to solve, and here's my system. So number 1, I got x plus y plus z equals 4. X plus y plus z is equal to 4. And number 2, I have x minus 2y minus z is equal to 1. X minus 2y minus z is equal to 1. And 3, I have 2x minus y minus 2z is equal to -1. 2x minus y minus 2z is equal to -1. And I put a line under it. I think I wrote it all down there correctly. So that's my system. So when you look at it, you look at opposites. So you want to see what will be the easiest variable to eliminate. And just when I wrote it down, I can see the easiest one to eliminate here is going to be the z. Why? Because in 1 and 2, the z's are exact opposites. And in number 3, it's just a multiple. So I can easily use 1 and 3 here to eliminate that one out of the z from those two. Okay. So in the first one, I'm just going to add 1 plus 2. 1 plus 2. And what that's going to do is give me new equation 4. So I'm going to add 1 plus 2. That will give me new equation 4. So when I do that, I got x plus x is 2x. Plus y minus 2y is minus y. The z's cancel out, is equal to 5. Okay, so see what I did to get that? So now I got one equation for my 2x2 system. So now what I'm going to do is go 2 times 1 plus 3. So I'm going to go, and I'm saying what I'm doing right here. So I'm going to go 2, hang on just a minute. So 2 times 1 plus 3, and that will give me new equation 5. Okay, so 2 times 1x is 2x plus 2x is 4x. Okay, 2 times plus 1y is 2y minus y is y plus y. 2 times plus 1z is 2z minus plus a negative 2z is the z's cancel out. And that's equal to 2 times 4 is 8 plus a -1 is 7. So there's my 2x2 system that I got out of there. And notice right away, it set me up to solve that by elimination. So all I got to do is add 4 plus 5. So adding 4 plus 5, I get 6x is equal to 12. So x is equal to 2. Okay. And then I'll go back into one of those equations there and solve for y. So if I go back into, say, equation 5, I get y is equal to 7 minus 4 times 2. So y is equal to 7 minus 8 is -1. So now I got the x and the y. So now I just pick any of the equations out of my original system. Let's pick equation number 1. That's the easiest one, and we can solve for z. So using equation number 1, z is equal to 4 minus the x, which is 2, minus the y, which is -1. So z is equal to 4 minus 2 plus 1 is equal to 4 minus 2 is 2. plus 1 is 3, is equal to 3. So now my ordered triple, x, y, z is equal to x is 2, y is -1, and z is 3. And there's my answer right there. So once again, to solve a 3x3 system, I write down the system, numbering all the equations, put a line under my original system. Then I look for whatever variable will be the easiest one to eliminate. So right here, the z's were opposites right away. So I picked that, okay? And the third equation had a z, which was a multiple of the first equation. So no big deal. I could then use those two equations, 1 and 2 and 1 and 3, to make a 2x2 system, which I did right here. So new equations 4 and 5. I added those two together. I got opposites there, and that canceled out the y variable, leaving me with the x variable. Okay, so that's the idea to solve these things. Now, sometimes it's not quite as easy as that. Let's look at another one here. We can start off with another one. So this is, did I get it right? 2 minus 1 and 3. Hey, got it right. So let's look at equation 3. So let's look at another one. So this is example 3. Good, which has a solution. But one of the answers is going to be a fraction. All right. So hang on a minute. At least we'll write it up here and take a look at it. Let me clean off this board right here. And then we can finish it next time. Good. Where'd my pen go? Where'd my pen go? Where'd my pen go? Oh, here it is. Aha. Okay, so this is example 3. Okay, so I'll write down the system. So here for equation 1, I have 4x minus 2y minus 3z. 4x minus 2y minus 3z is equal to what? Is equal to 5. Okay. And then equation 2, I have negative 8x minus y plus z. So negative 8x minus y plus z is equal to negative 5. Negative 5. And then finally, equation 3 right here. Should be a 3. 3 is 2x plus y plus 2z. 2x plus y plus 2z is equal to 5. 5. There's my system. So I wrote it down. So I look at it and I say, what would be the easiest variable to eliminate here? What do you think? I'm thinking probably the y, because right there I got dead on opposites right there. Okay, so if I do that, if I add just equation 2 plus 3, I'll get new equation 4. So just adding these two together, 2 plus 3. So I get negative 6x, the y's cancel out, plus 3z is equal to 0. Is that okay? Can it be equal to 0? Yeah, sure. 0 is a legitimate number, just like any other number. How are we doing? Oh, I got 1 minute left. So let's do the next one. So I eliminated y right here. So I'm going to go 1 plus 2 times 3. So I'm going to go equation 1 plus 2 times 3 and that'll give me equation 5 right here. At least we'll get the 2 by 2 system. So equation 1, 4x plus 2 times 4x is 8x. And then negative 2y plus 2y is 0. The y's cancel out. Negative 3x plus negative 3z plus 4z is plus z is equal to 5 plus 2 times plus 10. So 5 plus 10 is 15. So that gave me a 2 by 2 system. And we'll pick it up there next time. Okay, and we'll solve that one. I'll have to verify that and make sure I didn't make any mistakes. I did it quite fast. Okay, so any questions up to this point? Again, make sure that you get signed in over on the chat over there. Make sure everybody's signed in on the chat. Let me put this over here somewhere. There we go. Okay. And if anybody has any questions, you can sort of hang around and ask me any final questions, but that's all I have. And so we will stop the recording just here in a minute or so. Let's see. Okay, I don't see any other comments there on the side. Okay, any questions? Okay, good. Then we're going to stop the recording